Continuing on with our second installment of how do we keep the electricity flowing if we go to a renewable energy supply, a solar-based type renewable energy supply. And we said that one important strategy would be to have a intracontinental grid where we could exchange energy across the country, but also with our neighbors to the south in Mexico, where they have abundant solar and wind resources, and with our Canadian counterparts also up north. And to some degree, we already do that. There's a lot of electricity trade between Canada and the United States, and a little bit with Mexico. But the more we integrate all of that, the more likely it would be for any given point in time that there would be wind or solar somewhere, and that would be combined with hydro, which we could dispatch whenever we saw fit, assuming there's enough behind the dam to kind of balance that out. And we also added, importantly, that the wave energy potential for the West, especially the Pacific Northwest, is quite high, and it nicely balances out the summer and late spring peaks, early summer and late spring peaks in snowmelt hydroelectricity. So it gives us a winter peak. So wave energy would be the big thing in the winter, and hydro would be late spring, early summer. And then, of course, solar plays an important role year-round, especially in the Southwest. So those are all kind of important parts of our story. I wanted to add something about solar, though, and that is that if we go back to that set of graphs, or rather maps that exist, we can see here that, in fact, solar energy is by months distributed somewhat differently. But one of the things I wanted to point out, yes, in the winter, solar is definitely about the Southwest and South. Okay, no question about it. What's interesting, though, is by the time you get into May, June, July, August, and even September, you can see that the Pacific Northwest is pretty good, even here on the west side in July. In fact, we get more solar radiation in July than, say, Phoenix, Arizona does, or Tucson, especially compared with Tucson, in Salem, or even better yet, if you're in central or eastern Oregon. So it depends on the months. And solar is really great in a lot of ways because as more and more of us use electricity for air conditioning this summer, having that late afternoon sun at peak solar production, and also the demand for air conditioning is late afternoon and the evening. Solar does a nice job on the very first part of it, and there are solar electricity storage batteries, and there's also a solar thermal arrangement where they can release energy 8 hours after sundown fairly efficiently. So there's definitely the technological options there to make that kind of thing work. Okay, so let's go back to our outline then, and the more diverse our source types are, and the more geographically diverse they are, and remember, there's a seasonality to that. There's also a day and night piece to that. And so, like, for example, in Texas, they have an evening wind peak in the west part of the state and a late afternoon and in the early evening peak of wind on the coastal areas. Solar, of course, peaks in the middle of the day. And so there's some interesting patterns there. In the winter, that changes quite a bit for any state as well. So there's plenty of studies where they're basically balancing all of that out, figuring out how to plug all of that in. So this is doable. We need a national grid, and that's one of the things that's being discussed in Washington, D.C., is to do a big public works project building a national grid so we can exchange our electricity around. So somewhere it'll always be windy, or it'll always be sunny, or there will be enough hydro to fill in the gap, or we have other ways of storing, which we're going to get to, okay, for that electricity. Now, the second piece of how to do this is to go to conventional hydropower, dams, okay? So number two, the conventional hydropower. So basically that's how it works in the Pacific Northwest now. We release hydro when there isn't enough electricity, so kind of what they call peak power, or to firm up the power supply. But remember, we have a late spring peak in the Pacific Northwest. Okay, so that's when we have the most of it. But we also have our wind energy industry kicking in real well there. So that's again where the wave could do some really neat things for us in the future. So pumped storage hydropower. What is this? Okay, and here's one you probably didn't know. 2% of all of the electricity used in the United States comes from pumped storage hydropower. What does that really mean? Isn't that just regular hydropower? And the answer is no. Have a peek here. This is a look at the basic concept. We can take either one of these. I'm going to use this one over here on the right just because it's simpler and it doesn't necessarily require a river around. But what you do is you have an upper reservoir, you have a piping system, the water flows through here and generates electricity. Okay, fine. That doesn't really explain how it works, though, does it? You're thinking, how is this a storage thing? So here's what happens. Let's say that in the Pacific Northwest, we build out more wind power in the Columbia River Gorge and some of the other windy valleys on the other side of the Cascades. That's where it's windiest. Or we could also use this for coastal wind, which we haven't developed at all yet here in the Pacific Northwest. Coastal wind, which has a late spring, summer, and also winter, late fall and winter strong patterns. Okay, so you got, let's say you built up a big generation capacity, and there's a period of time or periods of time where you got so much that you can't even possibly use it all. What do you do with it? So you use that electricity, you flow it into the system, you pump the water uphill. Okay, so you pump it up here. Now it has that potential kinetic energy. You took the excess electrical energy being generated by wind or solar, or maybe even wave in the future, and you pump it, use that electricity to pump it up here, and then you wait until you don't have enough, and then you run it back through the other way, okay? And then it generates electricity again. So basically, anytime you have an excess, you pump it up the hill, and then when you have a deficit of electricity, you flow it back through, okay? 2% of electricity in the United States right now is generated that way. So that's pumped hydro. Lots of places you need, obviously, you don't want to do that on a flat plain area, it wouldn't work out so well. But anywhere where you have big changes in elevation over short distances and otherwise adequate water and so on, you can use a system like that. And it can be in river or off river, as that diagram earlier suggested. Another thing you can do, which is also proven now, we have the 2017 Tesla Australia example, is industrial scale batteries. And so just click on that, and that describes a little bit that whole story. But basically, they had a lot of trouble with grid reliability in Australia. They put these giant batteries, industrial scale batteries, in the system, and it is paying for itself in just a very short period of years. And it also does some other nice things for the grid, which is more technical than we need to get in here, but it's a great thing. And again, in that setting at least, it's cost effective. Anywhere where getting peak power at time, say for example that the peak demand for power in California is 4 p.m. or 5 p.m. Let's say that's an air conditioning demand. So that's within when, if you wanted to do a time of day pricing scheme with electricity would be the most expensive. Okay, so what happens now in places, Texas does this, they have that peak time of day pricing, and at that time they run these they're basically big aircraft turbines that run natural gas through them. They generate electricity using the natural gas for an hour or two or whatever it is, and they charge really, really, really high rates for that. So because those rates are so high, they're over 20 cents a kilowatt hour, you can, if you have a regular system where you're using batteries to store it, it more or less floats right now. You can pretty much compete. Some parts of California, we're starting to see this. You can compete with the natural gas on-demand generated electricity by just storing up the electricity sometime in the last 24 hours or so and then releasing it. the cost per kilowatt hour is about the same or a little cheaper. And that's kind of what happened in Australia. It's a more complex example, but this is feasible. It's already been done, and it was done 4 years ago, almost 4 years ago. Another thing that you can do is overbuild solar and wind capacity. What is that all about? Okay, so this is a little article on it. Just kind of read up a little bit on it. Overbuilding solar up to 4 times peak load yields at least cost all renewables grid. Okay, and so basically this would be the demand for electricity. This line, I'm going to zoom in just for a sec. I got to remember to take off the zoom later. So this is the demand for electricity, and so you put in so much solar. And by the way, solar is so cheap. We're going to get this later. We can actually do this. Okay, so this is actually what the demand is for electricity, and this is the supply. Way more. Okay, because it's cheap per kilowatt hour in the sunniest places. You can do that. Okay. And so what you do then is you have batteries that are discharging. See this battery discharge pattern? During these times when there isn't enough solar, you're discharging the batteries to supply the solar. So this is pretty much an everyday thing, okay? So this is where batteries are the most cost effective, is where there's a regular demand for them, okay? We're starting to see this in California, some in Arizona. So then when the sun starts to go down in the sky, eventually the amount of solar production electricity drops to very low and then nothing. And that's when again, the battery discharge system comes in and picks it up. Okay. So at these times, it's battery recharge or curtailment. You're either not using the solar at all, or you're just recharging the batteries. Okay. So this is the power to X conversion. That's the kind of dotted line down here below. So anyway, the basic concept, without getting lost in too many of the details, is just that you've got several sources. You've got wind here, see the blue, okay, a little bit of hydro, maybe in this case, but mainly you're using solar excess to store, and in the end, you get a system where you've got enough electricity to run the system, and almost entirely renewable. This one has a little bit of flexible gas. It could be a biogas or it could be natural gas as well, but it's not entirely clear from the diagram how that fits in, so we won't lose any time on that. So let's go back then to our notes again, and I do need to check in our timing. Let's see how we're doing. Okay, so overbuilding solar and wind capacity, you can see how that worked with solar at the regular pattern. You can also do that with wind. So if you have an area that has like a late afternoon, evening peak wind, which we have in the east side of the Cascades in the Pacific Northwest, you could keep building wind farms there. And there is already today, by the way, enough wind capacity to sometimes produce more wind. There were some moments in time a few years ago, I remember, where in the spring, there was actually more wind electricity being produced than was being used in the Pacific Northwest, and some of it they were sending it to California. But in more recent years, California has built up solar, so they don't need as much of our wind until their own sun starts to set, and then that wind becomes more valuable again. So if you overbuild both of those, because they've gotten so cheap, you can do that. And literally it means you might have to spill off some of that electricity, basically not use it, unless you have some way to store that, okay? And we talked about the batteries. But there's another way to do that too, and that's when you built that wind, water, solar generation capacity, when it overproduces, you can split hydrogen from water using the process of electrolysis. That's been around a long time. Okay, we know how that works. Hydrogen that you produce that, you're basically splitting the oxygen and hydrogen apart, and it can later be combusted or used in fuel cells to make electricity. So you either put it in a fuel cell to make electricity, so it's sort of like a battery, or you use it as a liquid fuel. You can make it either way, and then that's combusted, and you could run it through a generator to make electricity. So it's a great way to store, and you can store it for months, okay, even years. Of course, you wouldn't want to store it that long, but you could. Okay, so we'll continue on with number 7.